go ahead and get started. We're kind of also in between topics again for this, which is okay. We're still sort of finishing up this topic of privilege escalation and trying to connect it all together a little bit better than I think we were able to do at the end of last week on Thursday with regards to all these hash functions we were talking about and what does that mean from a user authentication as well as then from a privilege escalation standpoint. I'd like to think it'll make more sense after today. We shall see. And then we are going to jump into that next topic and get that started today before we continue that later this week. This is where we left off. This was just a human-readable version of the etc shadow file, sort of the conventional standard way to store the password information in Linux. One thing I think you should have as your takeaway in terms of just big picture things, we have these hash functions, right? The idea is it's a one-way function. Take a lot of arbitrary data, chew it up, digest it down until it's some manageable amount of data, 128 bits, 256 bits, something of that nature. For the purposes of password, we also apply these type of functions to our passwords as well. The benefit there is not necessarily decreasing the amount of data we store because oftentimes your password won't be that many bytes of data in the first place. The idea behind that, the benefit of that is it still has this sort of one-way concept behind it. You can go from password to a hash value, but not necessarily easily in the other direction. And then also you're never actually storing the password on your system. There's no file in your Linux system or Windows system that says username and here is the username's particular password. It'll be stored in some sort of format like this. Now, whether, we talk about this a lot, whether these particular fields are all that super important or not, it's hard to say. General awareness so that this doesn't look like kind of magic or nonsense, I think should be your important takeaway. So we have the username, we have some sort of encoding of what method is used for the hashing of the password. We have the actual hash value there kind of highlighted in orange. And we also have that salt field. And I talked about that on Thursday, and I don't think I explained it very well based on a couple of valid questions I received afterwards. The idea of having a password be salted is that you're not just having this kind of deterministic from password to hash result that is the same for every user that has the same exact password. You are basically adding some password to the input password before you apply that salt value for each of the users. It has to be something reasonably random, but that's about the only property it needs to have. The salt value would be different for every user on a given system and also different for the same user across different systems. The only value it's adding is such that if we happen to have the same exact password on the same machine, the hashed result is still going to be different. But otherwise, it is just an additional bit of information that is also just being fed into that same hash function here. That is the value of salting your password. There's some other values in that it just adds a little bit of the computational complexity of cracking passwords because it's not just input password length that one has to worry about. It is also that additional amount of information that one has to take into account. So in some sense, it's just adding extra kind of free complexity, free length to the end of a given password. But that's all that it's really doing. So you have your password, you've specified it. We take that. We also then take some additional sort of system-generated information, and that becomes what gets fed into our hash function when we have that salting there. But because of that, we actually have to store that value. There either has to be some kind of reversible algorithm for generating it, or as we are storing the hash, we actually have to know what that salt value was to be able to replicate the hash. When you do authentication, when you log into the machine, that same exact hash function then gets calculated. Take your password as entered, apply, concatenate the salt value that is already stored that you look up and check, apply the hash function that is specified. Only if that orange matches what gets calculated, was it a correct password. That has some benefit. We talked about how we hashed in Joseph Zambrano and Joseph Zambrino, right? Slightly different spellings of my name, and the hash value was totally different, right? That's intentional, that it kind of disperses the output given small changes in the input. That is a benefit for this as well. at least in theory, when I type in my password and it is wrong, as an attacker, I should receive no feedback as to how close that password was. It should look as random as a password that's very close, or as random as a password that's extremely far off the actual password. That is the benefit of what maybe makes something a better hash function for these purposes. But at the end of the day, that is what is happening when you're authenticating. We're storing that information. We're not actually storing the actual password on the machine here. And Windows is a pretty similar story as well. You'll read a lot of Windows-related documentation, and it talks quite a bit about Active Directory and domain controllers and sort of basically third-party or additional servers that are there just to handle the authentication side of things. And that is correct, that is true, that is actually happening in most modern systems. But otherwise, for your own local workstation, for your own local account on your own Windows PC that is not authenticating to the Iowa State or other domain that you're connecting to, there is just effectively the equivalent of a shadow file on your Windows system that is storing effectively the same exact kind of information here. So it's different because Windows and Linux are different, but we can squint at it and see something pretty similar looking here. Here, this example would be an unsalted example. What is in storing in these two base 64 strings here are the two different versions of the Windows old school hashing mechanisms we talked about briefly last week, Thursday, where you take the password, you split it into these 7-byte chunks, you convert it all to uppercase, and you actually encrypt it using DES as a style of hashing, and that's what's actually getting stored here in that file. One takeaway from this, both the etc/shadow Linux version and the Windows Security Account Manager storage of that roughly same exact information, is this mechanism, while certainly I think superior to storing actual passwords on disk in any meaningful sense, is itself vulnerable at least to privilege escalation. Meaning, if we have legitimate access to this system, Windows system, or that Linux system, one threat model, one concern, one potential vulnerability path we have to be concerned about is a legitimate user on the system having additional access they shouldn't have potentially to these type of hash values, and using that to basically crack into existing passwords on the system. And we do that a little bit in lab. I think it's an example of something that we do in lab where it's just kind of magic and it just kind of works and we don't think all too much about it. So I wanted to talk about the John software we're using, John the Ripper. Really cool software, pretty good logo, I have to say for myself here. The assumption under this kind of privilege escalation is you already have some legitimate reason to have access to hash information, password storage, hash information on those systems. Either you have just legitimate access to the file given the controls that provided on that file, or at the end of the day, that information has to be available via these services that are attempting to do authentication. Perhaps you're listening to the hash values being passed in clear text as Windows can do in certain configurations, or you found some other mechanism by which you have that hash information. That's the starting point. This piece of software, that's its whole reason for existence, is for various different kinds of password hashing schemes. It's just an attempt to kind of effectively brute force what could be valid passwords for those stored hashes. So we basically did this exact series of steps in the lab. Unshadow is a utility that's packaged as part of John the Ripper here. We're actually just combining those two files together. I didn't talk about etc password. It's another file that stores user account information on your Linux system. It's kind of incorrectly named for historic reasons. So in the times before we did salting of passwords, that file is where the hash information would be stored. Now it still stores things like what user groups and what other account details are associated with your username, and then /etc/shadow is where the hashes are stored. It doesn't really matter other than there's some user information in both of those files. That first command just basically gloms those two files together there. And then we specify John attempt to crack this hash file with a particular word list here. So first and foremost, primary to that kind of cracking task is the assumption that there is some sort of input word list that it is churning through to determine which potential passwords actually are going to match the hashes that are found here. So for this approach, for this kind of privilege escalation, the complexity of your password does matter. The complexity of your password does matter for this kind of approach in terms of the number of characters in your password, in terms of the mixing of case and use of special characters, and all those quasi-annoying password requirements that different systems just have different restrictions on. Those are maybe all annoying. We dislike them. Historically, at least, the reason for those rules was specifically to kind of make this particular type of approach of password cracking more difficult. That's not to say impossible, just more computationally difficult here. The default order, what the John the Ripper does, is the so-called wordless mode. It takes in an input word list, which we can look at some examples, literally just a dictionary, a plain text file with just a series of words in it, and it takes that and just checks all those. And that seems kind of obvious. So if your password isn't a word in the dictionary, you would be okay. It also does kind of conventional, well-known password mangling rules it applies there. Source code is open. You can take a look at the kind of rules it applies. So instead of the word password, it's 5s instead of S's and 0s instead of O's and things like that. That sounds like you're being clever when you're doing that, but we can probably run the numbers and give ourselves an estimate of how much value that actually provides in terms of password complexity, right? Because yeah, there's a bunch of those one could do. Oh, instead of ones, I'm using exclamation marks or things like that. That's fine, but you're talking about like one-off things here, right? That every time you do that, you're like doubling the password space. Okay, we've doubled the password space 1, 2, 3 times here, and then a capitalization is 4, 5. Okay, that's 32 times the amount of passwords the tool has to check. That's not very many, right? So it increases it, but not by as much as one would think. These word lists are kind of incredible in some ways, and the company that kind of provides commercial licenses for John the Ripper also sells word lists as well, but these days one can just find word lists that you can just download and use for your purposes, including what we do in lab. Again, the trade-off is going to be how large those files are and how much the tool is going to have to churn through versus how much coverage it actually provides. I think, mathematically, there's no guarantee one can ever actually crack your password, but one can kind of run the numbers and say, well, there's 15 billion entries in that particular file here. I would try to click on that and see what would happen, but I bet it would kind of crash my laptop if I tried to open up that file. But that's a lot, I guess you could say, right? Still just individual bytes, so that is a lot of passwords being stored in there. It's on the order of billions of passwords being stored on there. And we can kind of run the numbers in terms of how much complexity that is, how long your password would need to be to kind of guarantee it's not in that file. And then it's not just, like I said, a kind of trivial approach in which if it's in the file, it's cracked. If it's not in the file, it's not. It takes those entries in the file as a starting point and takes kind of reasonable manipulations of those values to generate other likely passwords. There's other approach that tries to take other user login information and do that, and doing that. That's a single crack mode. There's also just effectively like the brute force mode, which is just try all the possibilities there. That does become intractable pretty quickly. We wouldn't want to try that in the lab. It'll work if your password is 6 characters, but if it's even 7 or 8, the amount of iterations that's going to take, grows exponentially with the length of your password here. But in general, for this approach, how complex your password is actually really does matter. So you may think your password is clever. If it's based on a combination of different words with a couple special characters thrown in there, it's still pretty likely that a password cracker like this would be able to break it. And it is really just ultimately a matter of time. How much compute power is thrown at the problem? How important is it for someone to have access to your password? In the lab, our goal was, can we keep this down to, how long did it take? 2 minutes? It wasn't that long, right? When we did the password cracking in the lab, try to keep it kind of reasonable. The other attack we did in Lab 4, referred to as sort of pass the hash attack, this was more of a, you could call it sort of a Windows, either vulnerability or weakness in design of their security architecture, that if the more modern sort of authentication environment wasn't provided, if that fails for whatever reason, in our case, because we never set it up on those machines, it falls back to the older landman NTLM password authentication scheme. And in that scheme, if it is some remote connection that we are attempting here, the actual hash values themselves just get passed in clear text over the wire. Trying to remotely connect to this Windows machine, regular authentication fails. By fallback, it looks for that hash value, and it's not quite as bad as passing the password itself over the wire, but it's basically the next worst thing, which is we just pass that hash value over the wire in clear text, assuming anyone can have access to that. Anyone can either read the memory space of a process that is processing that hash value, and that's what we do in lab, or just snooping the wire and determining the hash value, those bytes as they're sent along the wire. You then have that hash value, and as we talked about here, that is what you actually need, right? If you're just authenticating via just regurgitating that hash value, that's all you need to be able to authenticate as that particular user. And what we did in that part of Lab 4 is we used what was effectively remote PowerShell utilities to be able to run a remote command. And in running a remote command on that remote Windows computer, we said, here's my user, and here's the hash associated with that user, and that was considered valid to authenticate as that user. That is really just more like a visualization of the hash functions in work as they're working versus something that a modern system would necessarily be vulnerable to. It's kind of a classic attack on hash functions and hash values. Without having to attempt to crack the password at all, we still don't necessarily know the password of that user that we used for that part of lab number 4. Finally, when we talk about privilege escalation and passwords, all of what we're doing here with cracking passwords and things like that nature aren't necessarily vertical. It's not necessarily increasing our privileges. It's just providing us with more privileges on the same system. You have an existing account with an existing set of privileges. You are now maybe getting access to someone else's account with a different set of privileges. Whether something is vertical versus horizontal is kind of semantics, but you can think of it as vertical as being more access. So if you were a regular user, privilege escalation vertical means you are now a more administrative user on that same machine. So that would be a reasonable target. If I somehow, as a regular user, I have some access, but now I have access perhaps to the shadow file or the SAM file, and I have access to these hash values, my goal would presumably be, how do I crack the administrator password or the root password on that system, or some other user who has additional privileges on that same system. So kind of a textbook definition thing. Vertical, that just means a user with more privileges, can do more things on the same system. Versus horizontal is just someone who perhaps is the same restricted type of user you are, but could have access to maybe their own set of files, or maybe just a slightly different set of access than your current user has. Generally, this would require some additional vulnerability or misconfiguration to be allowed to happen. A well-configured Linux system, for example, does not allow a regular user to view the etc shadow file. And I think hopefully we can see why that would be the case, right? The whole point of that file is it's encoding all the authentication mechanisms for all the users on the system. If we allowed all users to access that file, well then in theory they could run that same piece of software to crack passwords on the system. So we have this idea of these passwords and authentications and getting additional privileges on a system. It can involve passwords and it can involve cracking hashes and things like that. But usually it also then has to involve some additional vulnerability or misconfiguration on the system, because a well-designed system would not allow you to be able to do that. It's kind of self-defeating if that was otherwise the case. One such misconfiguration that we kind of bring up a toy example in lab number 5 is the use of the sudo command, super user do, a very well-regarded Linux utility that allows normal users to execute some code as the super user, as the root user. This has all sorts of potential benefits. We talked about this a little bit. Just for example, right, we have the nmap command, right, and we use nmap. And nmap has certain modes that regular users can have access to, and other modes that craft custom packets that only privileged users are allowed to do on the system. Well, it could be the case that I am providing you an account on the system, and I want you to be able to run nmap, but I only want you to be able to run nmap as a super user. So I would not want to give you root on the system. No offense, I just don't trust you. I don't believe you won't break the system if I give you that. So this process, this super user file, super sudoers file, allows me to specify those kind of policies. Like many Linux configurations, this was designed in a time when people were just more trusting or maybe assumed higher level of like technical competence. It's kind of a crusty old way of encoding that information. I specify the user, I specify what accounts they're associated with, I specify what commands they're able to run as super user, and if I'm not careful, I accidentally give them way more privileges than I actually intended to. But that is something we also do in Lab 5, where we have our own user that has no super user privileges, but we recognize by looking at that etc sudoers file that yes, some other user on the system themselves have more privileges to run things as super user. So we kind of do a hop, skip, and a jump there. A horizontal jump from user A to user B, and then from user B to our super user because they had that privileges to do that. The other command that you'll see is just su substitute user or switch user, I hear it referred to, that allows you to kind of just switch which user you're currently executing code as on the shell. The root user is allowed to, in most systems, run super substitute user without entering a password, but that would be a problem if regular users were able to do that, right? If I could execute super user do substitute user without any restrictions there, then that kind of just defeats the whole purpose as well. My first command would be switch to the default user, switch to user 0, switch to the root user, and all of a sudden, because of our misconfigured system, you have root access on the machine. But sudo is itself a very powerful kind of thing, and so it is something that will probably always exist on Linux-based systems. The other thing you do see in your configuration on these systems is not explicitly running the command sudo as such, but that you as a regular user are given permission to execute regular executables that themselves have the super user bit set. So if you ever look at the permissions on an executable, you have the RWX, and we've kind of played around with that this semester, right? Do I have read access to a file? Do I have write access to a file? Do I have execute access to a file? There's 3 sets of those for the user that owns the file, for the group, and then for all users. There's also that additional bit that sometimes would be labeled as an S here. And what that allows is any user who's allowed to execute that software is temporarily given basically super user privileges while they are executing that file. That is seen as kind of a workaround. Nmap could be an example, although you don't normally see it configured in such a way that here is one utility that does need basically super user access to do the kind of the fun things it can do. So what I do is I specify as I've installed it that any user who runs this application is temporarily granted effectively the permissions as a super user. That is something we also play around with Lab 5 in that you have to be really careful when you do that. And Linux distribution managers probably are pretty careful with what applications, what utilities they give the S bit to, the super user bit associated with those applications. But the example we do is let's just create one, let's just have it be somewhat trivial and show how the user can be changed through the execution of this otherwise sort of unrelated application here. For better or for worse, there's an XKCD comic for every single subtopic in this course. So I'm going to include them when I find them, sorry. Another example escalation we played around with in the lab, but I don't necessarily know if it made much sense to you as you were doing it, was this dirty cow vulnerability here. It's a good example of something that has since then become a lot more common, which is It's not no longer sufficient for someone to discover a fun vulnerability. It has to be a fun vulnerability that also has kind of a catchy name, and a fun vulnerability that has its own sort of dedicated website associated with it. This is one of the first examples of it. But it is a software vulnerability that was around for a very long time in the Linux kernel. We're talking a decade, and decade on a block of code that was very thoroughly reviewed and well understood still had a pretty significant vulnerability in it here. And what was interesting about this CVE is at the time it was sort of discovered and published, effectively every single Linux machine in the world was susceptible to this exploit. So, and I guess the other thing that made this a little bit more interesting than maybe some other vulnerabilities that otherwise would have a very high CVSS score is that the proof of concept exploit, like the one that you do run in the lab for this, was pretty straightforward, didn't require some of the darker arts of understanding how to build these exploits here. The main vulnerability in the dirty cow was a so-called race condition, and we haven't talked about race conditions as one of our CWEs, but it's another pretty important one that turns out just in practice of writing modern multi-threaded software is actually really difficult to prevent. And it just seems like, as we talked about with things like our use after free bugs, and we talked about buffer overflows, a couple of things we looked at, and we said, oh, I would never do this in my software. This is another example that it just turns out in practice that there's lots of advantages of writing multi-threaded parallel software. It's sort of a necessity for building modern software and certainly modern operating systems. And it turns out that as our understanding as sort of a collective software development community has evolved over time, it turns out to be a very difficult thing to go from a mindset where you're writing software that is just single-threaded. And I'm guessing most of the software you've written has been single-threaded. We start with main, we work our way line by line through until we get to a return or an exit. Whereas most modern software needs to have multiple threads doing multiple parallel work. And it just turns out that in practice, and I don't know, fundamentally why humans maybe are bad at this, it can be very difficult to write correct multi-threaded code. We usually want to have multi-threaded code in which we have some sort of shared resource. I have thread A and I have thread B, and the whole point of having thread A and thread B is that they're collaborating on something. Otherwise, one thread might have been sufficient for it. Thread A is doing some bit of work, thread B is doing some bit of work, and they're sharing some information along the way. That's just kind of fundamental in multi-threaded or parallel computing. It's not an accident that winds up being an issue we have to concern ourselves with. And in practice, these type of weaknesses resulting potentially in vulnerabilities are still pretty prolific in modern systems code, which in this case is you have some concurrent code sequence that requires that there's some exclusive access to some resource. That's very highfalutin sounding. You have some location in memory. You have a variable that both threads potentially want to access and update a variable. That's all we mean by resource here. It could be a file, it could be a device, just say some variable is fine. And depending on how the code was written, we have a race condition in which code 1 or thread 1 is wanting to read the value of x, and code 2 or thread 2 is wanting to update and write the value of x. And what the actual value of x is going to be, and here it's showing kind of time progressing here, really depends. Depends on which one happened first. That's why we call it a race condition. So threads are racing to compete. One is trying to read, one is trying to write. Which one actually happened first? Was it a read after a write or a write after read? Any of you in computer architecture right now probably might be getting some flashbacks about that. Which one happened first? We don't know. What is the actual value of that variable x? It could be 1, it could be 3. Sometimes it's 1. Maybe the vast majority of the time it's 1. Maybe every so often, depending on what happened with these threads, the value is 3. Once you've taken an operating systems course and you learn about things like mutex variables and exclusive access to resource, you may think, well, then we would always do a lock and an unlock. And there are mechanisms in software enforced at the architectural level to kind of prevent this kind of thing from happening. part of the challenge is there's a pretty big cost from compute performance perspective in enforcing that. And oftentimes when we write our code, we write it in such a way that we think this would never happen. And oftentimes it'll never ever happen until it does. And that's why it's a weakness, that's why it's a bug, that's why it's potentially leading to a vulnerability. So what happens with Dirty Cow? It's a little subtle. It has to do with the file and page reading and writing mechanisms built into the Linux kernel that you request as a user that I'd like to read from a file. And for purposes of passwords and authentication and privilege escalation, I want to read from etc/shadow. What will happen in a Linux system even today is if we'll check permissions, and if you don't have access to that file, as that file is going to be mapped into memory, you'll be just given some sort of copy access to that file. You will not have access to be able to write and update and change that file. You would not be, because it would check the permissions, you would get a copy of the contents of that file, not actually the actual contents in the file itself. It turns out there is yet a separate mechanism for which, after I've requested access to the file, before I attempt to actually write something to the copy of the file, there's a command that says, it stands for memory advise, where I'm actually telling the Linux kernel, that block of memory you just allocated for me because I'm accessing that file, I don't need it anymore. You can get rid of that copy, which is also something that would normally happen. I'm wanting to close a file, I don't need it anymore. Underneath the hood of your fclose function, that madvise function winds up getting called. Well, it's available for the user just to explicitly call as well. It just so happens, and this is a bug, right? It's not something that was ever intended. This value of x in this high-level example here is also exactly what happens with whatever variable internal to the Linux kernel is determining whether or not the user should have write access to that file or not. It's just another variable. It's a variable that gets checked every so often. We have one function that would update that variable, another function in terms of just accessing the file that is also accessing that same exact variable. And if one sets up a race condition back when systems were vulnerable to Dirty Cow, eventually we don't get the value of x equals 1, we get the value of x equals 3 back out. And so if you look at this code, it's actually doing very little. There's very little going on in this code. It's the kind of code that maybe you wouldn't otherwise write too much. You're specifying the target file that you want to overwrite as well as the content you want to overwrite it with. It's doing the memory mapping to that block of file that you otherwise wouldn't have access to, and it's just creating 2 threads. Has anyone done p-threads programming before? Okay, good. One of us. Okay, a couple of you. Okay, good. Create 2 threads. Create one thread called that calls this function. Create another thread that calls this function, and let's have them race, is basically what they're doing. And if you look inside the code for those 2 functions, here's the one here. This is the one that is attempting to continue to write to that block of memory over and over again. It's just a big for loop. Just keep writing, keep trying to write over and over and over and over again. So, right, that's for I equals 0, I is less than, pretty big number there. What do we got? Large number, 100 million. Try 100 million times to write to the file. It should fail every single time. Checking this race condition variable, don't have access, don't have access, don't have access, don't have access. Then we have this other thread that the same amount of time is saying, I actually don't need the memory anymore. I don't need the memory anymore. I don't need the memory anymore. And it just so turns out, and it's a bug, right? There's no other explanation for it other than that, or was a bug in the Linux kernel, that the order of those can be in such a way that it destroyed the copy, didn't check again if you actually had access to the write to that file or not, and consequently, one of these winds up actually working. Once you have access to kind of arbitrary files, well, if you could give yourself write privileges where you were only intended to have read privileges, what file would you consider updating first? /etc/shadow, /etc sudoers, all those kind of files now become fair game for you to kind of overwrite. Now you have proper privilege escalation on the systems. If we were to look at that CVE and the CVSS score, it wasn't that high for that reason. We played around with that score a couple weeks ago because you did already require some legitimate access on the system. And that's considered less of a concern than if someone remotely could just connect to your system and provide themselves that level of access. But in terms of modern Linux servers, in which very commonly we have many users with many different levels of permission, this was a pretty big vulnerability that had to be patched effectively overnight back in that time. And these days, all the interesting vulnerabilities have a cool logo and a fancy website, but this was one of the first ones. In terms of what are our countermeasures for password cracking, password reuse is probably the biggest one that one has to watch out for. You're really combining your mental trust models every time you reuse a password, that the password found in one data breach won't then be piggybacked upon to then lead to providing access to another password breach. The Have I Been Pwned website is a good starting point for that. Trying to use strong passwords. I mean, although, again, what is strong is kind of a debatable perspective these days. Try to avoid sticky notes. Multi-factor authentication seems to be kind of the default these days. It has its issues as well. It turns a knowledge of vulnerability into sort of a physical device vulnerability that one has to watch out for. For many of us now, our phones is the most important thing that we actually own in terms of our personal security. Somewhat debatable advice that you will see is the use of password managers to kind of keep track of all your passwords. That's certainly better than sticky notes, and lots of my colleagues in this department use sticky notes for their passwords. So don't actually do this, but when you go into one of your professor's office hours, look for the sticky notes, see what passwords you can discover, report back to the class, but don't actually take advantage of that information. But a password manager is basically a third-party sticky note, effectively, right, where you're trusting another resource to kind of keep track of these for you. On the Apple system, you have Apple Keychain, which is using full disk encryption. It's probably better. Someone would have to invest serious resources to be able to crack your password off a system. Also debatable is, I would say, changing passwords frequently and regularly. That is advice that you will still see people give, may lead to bad habits, right? We had a certain system that is no longer in place here at Iowa State where we had to change our password every single month. And I've been here for 20 years. I can only think of so many interesting passwords, right? So eventually you kind of start to recycle or make trivial changes to the prior passwords because, how many passwords can one actually come up with? On the flip side, there's some passwords that I've had in use for 20 years. Probably not a great idea either. It is reasonable fair game to hack me this semester as long as you don't cause any actual damage. I should repeat myself there. It's okay as long as you do not cause any actual damage. As I mentioned, I wanted to kind of switch topics. I know it's annoying when we do that, but otherwise we're falling a little bit behind. Questions about passwords before we continue? Okay. I know we're churning through some things. My goal is to kind of connect what you were doing in lab with kind of the textbook material for this type of topic. And the lab is fine. You're learning use of these utilities. You're actually proving concepts that these things actually can work in practice. But again, my impression is that it's a lot of do this step, now do this next step. And so my goal is always, when we have this time together, first off, it's not to waste your time, but secondly, it's okay, here's what you were doing or will do or have done in lab. What does it actually mean? Why does this work? What is actually happening underneath the hood? I understand we look at the source code for the dirty cow exploit and 2 minutes of reviewing it isn't sufficient for you to become an expert in it. So we stay at a high level within reason. Understanding some of the weaknesses in software is still really relevant, even if you yourself will not be writing software for a living, because that's where these vulnerabilities come from. So whether you're writing the software or not, the software we are using and the vulnerabilities that, despite our best attempts, still persist to this day are pretty relevant, are pretty important for you to have an understanding of. And that connects to this topic as well, that we kind of carve out web application security as a separate topic from just software security in general. But one thing I think you'll catch on to pretty quickly is it's really just a special case of what we've already been covering. We've already been talking about networking and protocols. We'll talk about web networking, web protocols. We've talked a decent amount about software vulnerabilities. We're going to continue to talk about them. It won't be C code anymore, at least. It'll be web software vulnerabilities and corresponding exploits. I think what warrants and why your textbooks in this material have one, sometimes two chapters on this is just the ubiquity or the importance of web applications. So it is just software at the end of the day. So it is in some sense the same exact topic as understanding vulnerabilities. It is such a prevalent piece of software. It's such a critical piece of software. And some of the characteristics of the attacks themselves are somewhat unique to web applications. That's why we look at it as a separate topic. But when we look at the web top 10 vulnerabilities, it's going to look somewhat familiar to the common weaknesses that we're talking about in software, because it is just software at the end of the day. We do a little bit of that in the lab. There was a Flask SSTI exploit. That was another one where we just kind of copy-pasted something and saw what happened here. We'll talk about what that was doing in practice, and I think it'll make a little bit more sense as we get through this topic. Why do we care about web applications? Because there's a lot going on. It is all just software and resulting corresponding hardware platforms here. This is my perspective of web applications and their corresponding architecture. You take a web dev class, you may get a totally different view of it. It's also something that can be very framework specific, or people can have strong opinions on. This is just my opinion on what a web application tends to look like. It's got a lot of different pieces to it, though, more so than just a typical single user command line utility. And consequently, there's a lot of different places where we have to be concerned about the resulting vulnerabilities or security of the software running on here. First off, we have the actual web server itself. I'm very proud of that animation. Thank you. Sometimes you'll hear the term as like the front end. Here is the logic that is helping you determine how to present the content that you're visualizing, that you're seeing. You could think of it as the website and the server running the website, but it doesn't have to be a website. It could be an application that's using web technologies here. That's our first concern here. The vulnerabilities that could be in that actual web server itself. It's just a piece of hardware running some software at the end of the day, so it will have those vulnerabilities. It is communicating usually in a bidirectional way to your client device. That is your web browser or your tablet, your phone app, and that is communicating over a series of HTTP requests. And we'll talk about that. That is still kind of the conventional way we have that bidirectional communication. That is our application layer protocol for doing that back and forth. Here's my request, here's my data back, and the kind of things we can do with that are quite a bit more advanced than maybe originally envisioned, but it's sufficiently flexible so that we can run pretty advanced looking applications using this kind of infrastructure here. But that is your web pages, that's your content style sheet, cascading style sheets, your JavaScripts, your API calls. Also part of that communication is depending if there's any additional sort of back-end logic here. You could hear this referred to as your back-end, if you can hear me, as the back-end, as the business logic, as just your application servers here. That usually is something, depending on your web architecture, that we don't necessarily directly connect to, that we have the web server acting as our front end for us. So our client device, our laptop, our phone, what have you, is connecting to our web front end. And the web front end may be separately having all sorts of separate business logic. Could be the same physical machine, could be all part of one web framework. It doesn't have to be physically separated, but can also be physically separated as well. That itself is also just a piece of software, could have its vulnerabilities that we have to be concerned about. And then depending on our kind of storage needs, and here's where you take whole separate classes that talk about what this type of software has to do and what it looks like. But that itself has its whole separate host of security concerns as well. So your database, whatever backing storage you have, your data warehouse, your cloud storage. Those of you who are in software engineering get the chance to take multiple classes in this area. We will talk about it a little bit because there are real security implications of that indirect connection between our user on the client device and some SQL or other database that's kind of having our backing store here. One takeaway from this is kind of effectively every stage along the way, there's potential web vulnerabilities here. We kind of combine that all into one big bucket. So when someone says web application, it could mean many, many different pieces of software, right? There's the client, there's web server, backend, database server, and with a lot of potential interactivity between all those pieces, a lot of potential different ways for what are ultimately the same kind of software vulnerabilities to be present along the way, because it's ubiquitous, because it's important, because there's a lot of complexity there. We look at this as a separate topic than just software security in general. And it's not just our opinion, it's a very common thing that people do. I think we know this because we talked about HTTP. We did some very quick little netcat examples where we connected to an unencrypted HTTP server. But HTTP stands for Hypertext Transfer Protocol. It's still the standard method for doing communication between web servers and our clients. Started all the way back in 1989. There's Tim Berners-Lee, who's the inventor of the World Wide Web, HTML, HTTP, and URLs. The most common version, I put an asterisk there, is still HTTP 2, which was introduced in 2015. There is also HTTP 3, introduced in 2022. The other term you'll hear used for that is called QUIC, which used to be an acronym, but it's basically just parallel UDP connections versus TCP connections. I put the asterisk there as HTTP 2 being the most common version in use today. That is quickly changing. I actually don't know as of literally today if QUIC has kind of gone beyond 50% uptake. As Google's using it more and more, and as Meta is using it more and more, that is a pretty high percentage of overall internet traffic. So it may be the case that we're actually more commonly using QUIC than we are using HTTP 2 today. And then we have kind of the secure variant of HTTP, which also has multiple iterations, but loosely grouped into what's called HTTPS, which is HTTP with our secure sockets level or transport layer security. In general, there's, yeah, go ahead. It's significantly different, and I don't actually know all the details of how it works. So we know how TCP works, I guess, at a pretty high level. And ultimately, under the hood in TCP IP is this single kind of client-server connection here. Request, connect, handshake, start transmitting data back and forth. QUIC, I think, was designed from the ground up with the recognition that a large amount of web traffic is things like video and things of that nature, in which, while we think of TCP as being necessary because we need every byte to be correctly, securely transmitted along the way, if X% of our traffic is actually video, UDP may actually be the way to go. And so QUIC used to stand for something like independent UDP connections or something like that. It's not an acronym anymore. The idea being that when I connect to the Facebook app and I'm watching a video, it's actually not just opening up one TCP socket, it's maybe opening up a couple dozen UDP connections between myself and the server. That is the limit of how much I know about it. I've never actually looked at the source code for it or anything like that. But the idea is it's kind of a trade-off, a small trade-off of reliability for just taking advantage of just modern bandwidth and modern bandwidth needs as well. So when I mentioned that it's potentially the most common version in use today, there's just specific very popular applications that are now using it. A lot of cellular traffic, I guess, uses QUIC because that's also a good match for that for whatever reasons. So percentage-wise, it's a very difficult thing to know for certain, but I've seen arguments both ways in terms of how prevalent it is versus just traditional old HTTP. Either way, even with QUIC as well, you still have this client-server model, where in our case, the client would be our web browser or a mobile app, and the server is our web server, and there would be a request still to connect to the web server. We still, by default, use our port 80 for HTTP or port 443 for HTTPS, and there's going to be a series of those HTTP requests back and forth. I request data, I get data back out with the requests that are encoded via those uniform resource locators, better known as our URLs. Let's leave things here for today. We'll pick it up on Thursday, hopefully with fewer cable and chat interruptions. We can make a little bit more progress on Thursday. So if I don't see you this evening at the open forum, I will see everyone on Thursday. Thanks.